Hi, everybody. I'm George Fairbanks, and indeed, we're going to make you guys work a little bit today. So first of all, I want to congratulate you for falling for the clickbait title. There is absolutely no invasion of functional programming into software architecture, but it sounds a whole lot better than an interesting exploration in the intersection of two domains that are popular today, or some such boring title. So you get the clickbait invasion title. And then the second thing is I want to let you guys know that I have gigantic imposter syndrome this morning. People have been working on functional programming since the 60s. And there's a huge depth and an enormous amount of formalism, and there's a lot of expertise in different languages. Maybe some of you guys have dabbled in these things or are experts in them. I think I know something about software architecture at this point, and I wanted to talk about the intersection because I've been digging into this topic. But basically what I'm saying is when I get it wrong, come find me afterwards, and then I'll make the next talk better. But I can certainly talk about what I've figured out. The other thing that I'm definitely not an expert in is in user interface design these days. I mean, I have built user interfaces in a variety of different technologies, but it hasn't been my full-time job, and as you guys probably know, there's an enormous amount of depth and complexity in each one of these things too. So with the caveats out of the way, let's actually talk about some interesting stuff. The reason that the topic of functional programming I don't believe has been a common one at Saturn is that we, since the 70s, have been segregating two different ideas. One is programming in the large, and the second is programming in the small. And the way this traditionally goes is something like there are concerns that go on when you're typing an individual method or function or procedure in your programming language of choice. We're going to call those programming in the small concerns, like variable namings and things like that. And then there's the big picture stuff of like how do all my modules or components or runtime systems, how do all those things get arranged? And we consider those architectural concerns or programming in the large concerns, okay? So when someone suggests that functional programming is related to software architecture, your first concern is like, I had already segmented that in my head into the programming in the small bucket. So today might be a little bit interesting because I think we're going to find a lot of connections between the two. So you guys may have noticed at your companies that functional programming is increasingly common, increasingly popular. Perhaps the biggest telling point is that in one of the most conservatively evolved languages, Java, the newest version has first-class functions in it, and it has streaming operators and so forth. A lot of things that were carried over from functional programming languages, okay? So even in the traditional safe zones for object-oriented programming, we're seeing functional programming pop up. So that's something that explains that it is happening, but the question is, like, why is this stuff happening? Well, the first thing is, as you all know, the clock speeds on your computers are not getting any faster, but you have to solve bigger and bigger problems. And so we end up with lots and lots of machines, which cost a vanishingly small amount of money. And if we could figure out how to solve those big problems with a lot of little chunks of computers, okay? Functional programming seems to be good for that. The second is that as our systems get bigger, and as you just heard in the keynote today talking about all the challenges of distributed systems, we as software developers, unfortunately our brains are not getting bigger as the problems get bigger with them, okay? And so every time we go back to the toolbox and we say, what toolbox, tell me what tools can I use to combat this complexity? And functional programming has always been there. But it's been one of these things we haven't reached for all the time because of a variety of different reasons. One is the perceived connections with like obscure math that I'm never going to get, and other ones might be that I have to burn a lot of RAM, or it might not be as efficient per core to implement, but these things are more viable now because of the complexity. And then finally, and this is one that's a little bit shocking because I had this intuition in my gut that said that servers in a cloud provider are really cheap these days, and so I actually went and did the computation, and you can find out, you can rent 100 machines for the entire year running nonstop for less than one junior developer salary. And guess what? It's going to be cheaper next year, okay? And so the point is that I phrased it as we have more money than sense, but I mean, this is almost literally true, is that if we can throw computation at the problem and stop thinking about it, great, okay, and we are increasingly doing that. Like, how many times do you guys run your tests before the code goes into production? Remember in the old days when you would do like one really big regression test before it went out? Like we don't do that anymore. We run the regression tests all the time. In fact, many times before it goes out to production. So it gives us opportunities to do things that were prohibitively expensive in the past. So I think this is, in general, the way to characterize this talk is it's a new perspective on old ideas that are increasingly being used, okay? That we see a bunch of programming language constructs, functional constructs in mainstream languages, and we're actually, maybe at your company as well, seeing a renewed interest in the purest languages, the MLs and the Haskells of the world. And so I think that it's fun here at Saturn to chat about, well, okay, those are the ideas from functional programming. How do those apply to software architecture? And the reason the paper's on the right here is that people have been arguing about this stuff since the 70s, saying, hey, come on, it's time, it's time. Maybe the time is actually coming. So as a bit of fun, and as Elcho mentioned, we're going to do some group exercises here. You know, when I started this out, I said, like, how can I assume that everyone is going to have a laptop? And then I realized everybody has a cell phone. Does anybody not have a cell phone in this room? Okay, everyone has a cell phone, right? This is great. Okay, so what we're going to do is we're going to play a little functional game just to get you into the spirit of doing functional programming. It's called Cube Composer. But we're going to do something else later on, and for that you need to download an app. Okay, so the first thing is, if you have a laptop, great. You don't need to do anything right this minute. But if you have an Android or iOS phone, if you could go to your app store, and I want you to type in RX Marbles. RX Marbles. And you can't click these links very easily, but the people back at home can. That's right, I'm talking to you. The only thing I'd suggest is please, once you do have downloaded this, and we've overwhelmed the cell phone network with everybody downloading at the same time, once you've got it downloaded, please pay attention to me, because my ego is fragile. And like if you're all sitting here playing with the marbles game, well then, you know, I'd be sad. So I'll give you guys a minute. Is everybody finding RX Marbles, hopefully? Well, if you don't find it, it's not the end of the world, because we're going to see it on the screen, but it's even better if you can play with it yourself, because learning about these things, it's one thing to see it statically or have somebody explain it. It's another thing to actually be playing with the functions yourself and see how they work.
I don't have a phone.
You have a phone right there.
That's Microsoft phone.
Oh. Did you hear that, Michael? Where did Michael go? Okay. Well, I didn't say that. Okay. So what we're going to do is, now that everyone's got the Marbles game downloaded, or at least it started downloading, we're actually going to play something a bit simpler to start with. This one's called Cube Composer, and the whole goal of this is, if you haven't been doing much functional programming, I want you to feel awkward, so like you did when CS 101, when somebody asked you to do something that you now consider really straightforward, but at the time you're like, how do I do this with a for loop or a while loop or whatnot, okay? So I want you to feel by the end of this that it isn't as crazy as you might have assumed. Let's see, how do I get back to this? So I gotta escape, and then I go to Cube Composer. And can everybody see this? All right. Okay, so this is a little game. It's written in JavaScript, runs in your web browser. You can just go to this Cube Composer, links on there. And what we've got down here at the bottom are some operations, some functions that we can apply to the bricks at the top. And over here is a goal that says we want to see a row of yellow bricks with a row of red bricks underneath. Okay, make sense as far as what we're trying to do? And so what we'd like to do is apply these operations, these functions, so that we can transform one into the other. So let's just try one of these. Okay, so the first one says map yellow to red. And so if I drop it over here, do you guys see what that did? Okay, that's sort of straightforward. Let me just drag that back. Okay, and let's say, what if we did rejecting the yellow ones? Oh. You see why that works? Okay, so let's try another one. Let's see, this one that maps a yellow brick to a red brick and a yellow brick. Okay, so let's try that. Okay, none of these got to the answer, okay? So, does anyone want to give me a suggestion for like what I should do to get to the end here? Okay, so you want me to do this one here? Okay, so I do that. Now I've got a row of red bricks. Okay, this one here. Nice. You guys see why that worked? Because the first operation took us from red and yellow just down to red, and then the next one took every red brick, or actually every brick, and gave me a yellow brick on top of it. Okay? So let's try another one. So hit next level. All right. So same starting point. What do you guys want to try?
Reject the yellow.
Reject the yellow ones.
And map
Stack the yellow ones.
the last one.
And then
Yes.
take every yellow brick and make it a red and yellow brick. Nice. One of the things you'll notice is that if you've been working with functions like this for a while, the solution pops out faster. In the same way, do you guys remember, like everyone I think had a slightly different CS 101 problem that they would give you at the very beginning. But I remember one that it's been long enough that I was teaching myself on an IBM PC ages ago, right? So it was sort of self-taught at the very beginning. But a friend was in college and he was taking CS 101, and the problem that they gave him was a vending machine and making change. Okay, and the idea is that the vending machine only had certain coins in inventory, and so if you want to give them back 35 cents, but you got no quarters, you have to figure out what you can do with what you got. And so right now, you guys would think of this pretty simply, which is start with the biggest denomination coin you have, say, can I give them any of those? And if not, you go down to the next one, you say, can I give them any of those? And just walk down to the bottom ones and give them, until you're done, okay? Which seems like a perfectly reasonable decomposition of the problem, but for the students at the time, it was like, they're going crazy and it takes them a week to get this done. So my point is that I still feel pretty awkward when it comes to the functions, and I watch other people that are good at this and they just get right to the answer. So if you feel that way too, that's perfectly normal. Okay, so that's the cube composer game. So hopefully, again, this gives you an idea of some functional transformations you can do. Notice that there's no state in this, right? You have some bricks, you have an input, it has some transformations, and you have an output. And the idea is that you would be building up, functionally, some series of these operations from some primitives, and by combining those things together, you get from what you started with to what the computer is supposed to be outputting, okay? So, sorry, we have to go back to slides now. There are some big ideas in functional programming. There's a lot more ideas in functional programming than I think are really relevant for us in software architecture. So what I did was I sort of cherry-picked some of the ideas, and those are the only ones we're talking about. So for example, if you've heard about lazy evaluation in functional programming, which commonly comes up, I didn't see, obviously, where that applied at the architecture level, so it's not in the slides here. So the big idea here with functional composition is that you can build up a program by applying little functions until you get to the overall result. Okay, and so I think everyone will be familiar with the syntax that's on the left there that says g of f of x. The idea is that you take your input, which is x, you apply f to it, and whatever comes out of f, then you apply g to it. And many people have complained that this sort of feels inside out, that you have to, and you've seen this in any other language too, where you can nest the calls to subroutines. But there's another way of doing this, and the operators vary, but here's one of them that happens. And you can say, do f of x and then do g of x, okay? So has anyone done Java and streams these days? Okay, so it looks more like the second one, but what operator does it use? Oh, you put a dot between the methods, right? So you say method 1 dot, method 2 dot, method 3 dot, method 4, right? You can chain these things along, and then it's sort of easy to think about it because they go in the sequence that you see them from beginning to end, rather than, you can also do Java in the nesting parentheses sense, right? Okay, so the reason I bring this up is that we've already seen this a lot in software architectures, right? So what you see in blue here is a Linux or Unix command line where there's a bunch of independent tools. And when I say independent tools, I mean these are actually separately deployed binaries that are sitting on your disk, okay? And the reason all of those go together is that each one of them reads from a standard input, does some functional transformation on it, and then writes to a standard output. Okay? And that allows me to compose them, as it turns out in Unix, is you've got these pipe operators between them. Okay? And this has been a gold standard in many ways for functional composition and pipelines and late binding, and you make little tools that do one thing very well. Like there's a lot of mantra that comes along with this, and it's been very popular. Okay? And it doesn't mean that every one of our systems should work this way, but for a category of systems, it's a pretty useful thing. We also see similar kinds of behaviors with event-based systems. Okay? Usually the event-based systems are not a simple pipeline like this. They tend to have more branching. And machine learning systems, right? You take your inputs, you run it through your machine learning graph, and it produces the output. Or what we'll look at a little bit later, reactive systems. Okay. The second big idea here is that in functional programming, they look at mutation of state as being a weird thing that causes complexity, and I really would like to avoid it if at all possible. Okay. So what I mean by that is, we are so used to, I've got some variables, and my program changes the state of those variables until the program is done, and then I take maybe one of the variables and send it away to the next. Okay, is that the way you guys think about programming? Okay, so the argument is that if you think about the functions as not having any side effects and not holding on to any state, it becomes a lot easier to reason about them. Okay, so what I tried to come up with an example here. The first one is cleaner. The idea is that if you use the command line program curl to call a remote, use HTTP to call over to a server, and if the server had a function at number after and you gave it the parameter 5, it would return 6, and it would always return 6. There was never any question that if you ever called it at some point in the future, the number after 5 is anything other than 6. Okay? But it's sort of a lousy example. So I tried the second one, which isn't quite as good. And the idea here is, what if you said, let me get customer number 5? Well, if I say get me customer number 5 and it's version 1 of that customer, like before I've changed him, well then I always get version 1 of the customer, and I'm comparing that with what is arguably more common. You say get me customer 5, and if he was changed, the next time I call it, I get a slightly different version of the customer because I changed his address or I changed his name or something like this, right? And you can see that, I mean, the technology supports both of these two, and it's something that I would impose on myself. Now, the neat thing is, of course, if we use the first style, I can cache that result forever, right? I don't have to worry about it becoming stale, because version 1 is always version 1, not going anywhere. Whereas in the second one, and you guys have had to reason through this before, I'm sure, at some point, you're like, well, if I call it, but then I'm going to cache it for 5 minutes, but then I hope it hasn't changed on the server, and you're always trying to do this complex stuff, right? So that's the idea, is that the pure functions make it easier to reason through the problem. Now, statelessness is related, and it's also related to immutability. So the argument is, if there is no state, then all the instances are equivalent to each other. Now, we've been doing this in architecture for a long time, like even since the days of the Java pet store. Remember that back in 20 years ago in the late 90s? And they're saying, here's how you can set up all your beans to do different functions. And they had stateless beans and stateful beans, okay? And a lot of people were arguing for stateless beans in the middle tier because what you would do otherwise is when your customers were coming into your web application, you would route them to the stateful bean that knew about the customer's context, because what you'd done is you'd done this expensive, slow operation of loading the customer off the disk, and you're holding it into memory. So you'd really prefer to keep hitting what we called stickiness onto the same middle tier, okay? And the alternative was abandon that idea and just say all the middle tier stuff is stateless, which means that if I need to support more customers, I just put in more instances in the middle tier. This is an idea that's very common today, okay? So the idea is if they're all equivalent and have no state, I can have as many as I want or as few as I want. Now, immutability is a little bit different. It says you can have state, but if it never changes, that becomes really easy to reason about as well, okay? And you heard that a little bit in the event sourcing and so forth. Now, imagine that I have a middle tier, but I push some state into it. No problem. As long as that state never changes, again, I can replicate that as much as I want. idempotence is a sort of a, it sounds very mathematical, and indeed it is. But the idea behind it, especially as it applies to software architecture, is really pretty simple. Imagine I had a bunch of computers that were resizing images. This seems to be a common problem that always comes up in examples. But if I said, take a picture and resize it to 100 pixels, okay, and put it back in the same place. And so I've got a disk and I've got a bunch of computers that can resize photos. If I always resize it to 100 pixels, if I accidentally do the same operation twice, no big deal. It's idempotent because it's going to get the same result no matter how many times I apply it. On the other hand, if I do the one on the right, which is pick up the picture, make it half the size it was before, and then stick it on disk, if I accidentally do it twice or more times, I'm going to get a smaller and smaller picture each time. So the second one is not idempotent, okay? Hopefully you guys have seen that kind of thing before. There's a similar sort of thing. Remember in the old days with a web application, and it would say, please don't click the submit button twice, otherwise you'll buy your shopping cart twice and you'll be angry, right? You guys remember that kind of old days? Okay, so how did we solve that problem? Well, there's a variety of different techniques, but one is to put an ID on your shopping cart, okay? In which case, you can say buy shopping cart number 5, and if you say buy shopping cart number 5 again, it's still the same shopping cart. It's not like Amazon gets confused and thinks you wanted to order shopping. If you took the number 5 off of there, all Amazon would know, it would say, you know, buy toilet paper, buy toilet paper, buy toilet paper, and you suddenly have a lot of toilet paper at home. In which case, you could go to Costco, right? The reason that this comes up a lot of times is, one, we already saw the duplicate request detection. And second is that if you have a lot of work to do and you farmed it out across a lot of servers, you can't always be sure whether you sent some work and it's just taking a long time, or if it's actually stalled or the machine crashed or whatever. And so a lot of times what you do is you just go ahead and schedule it again. Because if you've made the work idempotent, it doesn't matter if you schedule it 20 times, you're still going to get the same result, okay? So that's the big idea there. The final idea is a bit slipperier, so it may take a little bit longer to explain this, is that with functional programming, you tend to think about definitions rather than procedures on how to get something done, okay? So if going back to that cube composer, writing, I think for everybody in this room, writing a procedural description of how you start with the input and transform and the output would be perfectly straightforward, right? Like, because we're super familiar with this. But thinking about it definitionally is a little bit trickier. And so the example I like to use here is about painting a fence, okay? So imagine you hire a painter and you say, how do you paint a fence? He goes, well, you pick up the paintbrush, you dip it in the paint, and you put the paint on the wall, and you keep repeating until you're done. Like, what's so complicated, buddy? And then you say, well, you know, I've got to buy the paint. And it turns out I'd like to know how much paint to buy because I can't return the paint because it's a custom color or something like this, okay? So I'd like to know how much paint you're going to use. And he goes, look, I just told you, you take the paintbrush, you stick it in the paint, and you put it on the wall. And he's just like, I don't have a theory, I don't have an idea, I don't have a definition that tells me how much paint that I need, okay? And so instead, if you're a functional programmer, you might tend to think about the problem this way, which is you have a wall, and you have paint, and there's a function that maps the paint onto the wall, okay? And paint has different characteristics, like maybe brand A only needs 1 coat and brand B needs 2 coats, okay? And the other dimension might be, I need to know how much area the wall is. But somehow if I know what the coverage is on the paint and what the size of the wall is, there's a function, I haven't figured it out yet, but there's a function between those two things and a completed wall, and maybe then I could figure out how much paint I need, right? So my point being is that this procedure works perfectly fine. I'm not trying to say that doesn't work, but there's a style of doing things in functional programming where you get closer to a declaration that says there's a mapping between this and this, and therefore you can answer different kinds of questions, right? Like how much paint I'm going to need. All right. How's everybody doing so far? Okay. I can't quite tell. The room is a bit, well, it's also early. But don't worry, we're going to do some, what's that?
It's 11.
It's 11, not that early. Okay. So another topic that comes up in functional programming gets covered under the category called reactive programming. Has anybody heard about reactive programming? All right, great. Well, you can tell me where I get this wrong. Let me tell you a little story about how I got interested in this topic, and this might resonate with some of you, is that like many of you, you probably decided, look, I need to build a modern client-server application with the application running in the browser. And then you throw yourself into the abyss, which is JavaScript, HTML, CSS, modern software development, okay? And the people that are really good at this, they spend a lot of time and they know where all the nooks and crannies are. They know which library has become incompatible with what library. They know what the new hotness is, and they know, please don't use that old stupid library. Everybody knows not to use that. So I, of course, fall into this and have a huge amount of trouble. And eventually I decided, like, this is crazy and I should look for other things that people are trying. And it turns out they're applying functional ideas to user interface design. And I found some styles in here which are related to reactive programming. And there's a particular guy, Andre Stoltz, who's written about it extensively, and I've borrowed heavily from his expositions here on how this works. So this is what made me realize that there's this connection between architecture and functional programming, because I had been taught the MVC style of doing UI design, which deals a lot with mutable state. Like, you come up with this graph of objects and you say, well, here's my model, and every time my model changes, it updates the view or something like this, okay? But the model then is mutable, okay? And then these events fire off, and you end up with troubles in trying to coordinate all those different events and making sure you don't have flickering in your UI and all the kinds of things I worried about 20 years ago. So this is my little experiment, or my dipping my toe in the water on how reactive user interfaces work. So what they recognized first was that the observer pattern is great, that I can find out about a stream of events coming out, and everyone here, I assume, is familiar with the observer pattern. But there's a problem. The first problem is that when something goes wrong, there's no mechanism for the observer pattern to say, something went wrong, okay, which seems pretty important, and it just isn't in there in the pattern. The second thing is that some streams go on forever, but some streams close, and they say, I'm done sending you input, you might as well shut down now. And so my advisor at Carnegie Mellon, David Garland, the first assignment in software architectures that he gives is related to this problem. And what he does is he has the students set up a pipe and filter system. And the way that the students often solve it is that there's some part of the code that's looking at the pipe and filter network, and it knows when the last input has been applied at the beginning, and therefore it knows it can turn off the program once it comes out the end. Okay, so there's some sort of omniscient thing looking at the entire architecture. And this is David's point, is he wants them to recognize that that goes outside the style. So if you think about those, the pipe and filter network on the Unix command line, none of those programs know about the other programs. That's part of the style. And so if the students don't go, aha, part of the style is you don't know about the other guys, then you didn't really get the lesson of what the architecture style is about. Okay, so what goes on here is that because we've extended the observer pattern to have the completion message in there, you no longer have to go outside the style or come up with a special value you stick on the stream that says, I am the last value. Okay? So this is the big idea, is that you have out-of-band signaling for errors and completion in the reactive patterns. Okay, so let's see how this would really work in practice. And this is the example from his document, which I highly recommend. The first thing is the primary thing that you're manipulating is streams of events. And a stream of events is a time series, list of events. Okay, so you don't know what events are coming up in the future, but you can see the ones in the past. Okay? Then you take that with a rich set of stream operators. Okay, so we saw that in the Cube Composer game, that there's some functions that we can pick up and apply to the problem. So what he's done here is, in this example, is we start with a stream of clicks in a user interface. And the idea is we're trying to detect double clicks. Okay, so how are we going to do that? So the first thing is we start with the raw stream of clicks at the top. And then there's an operation that says, Well, if you see any events within a sliding window of 250 milliseconds, then just clump those together, okay? And that's what we get in the second stream. So we take the first stream and we transform it into the second stream. Does everybody see how that works? Yeah, so the thing is about each one of these things sort of makes sense, but our brains are not really structured yet to like figure out how to get from A to Z. We don't know how to, we can see each of the steps, but we can't yet see the full path. So then there's another transformation that takes each one of those compound events and it extracts the length of the list and it just puts out another stream which has the number of clicks within that window, okay? And then finally, what you do is you filter that stream to take out all the single clicks, okay? Take all the ones. And the thing is, by the time you get to the end, you're like, every step makes sense. You can give yourself, it's like making an argument to yourself that like, yes, I believe that would indeed take all the click streams and turn them into a stream of double clicks, okay? Pretty neat. So this text on the left is meant to be just exactly that, is that we take the stream, we group the nearby clicks, we count the size of the group, and we drop the groups that have size 1. Not too bad. Okay. So he goes on to say that when you build user interfaces, you can actually compose them in this way. If you start with a problem that says, I've got clicks on a user interface, I can transform that into something more refined, which is double clicks in this case, okay? And that this is different than what model view controller used to do with a bunch of mutable state and, you know, it becomes tricky. Everyone talks about this, that you're running your program, then you need to make a remote call to the server, but when the data comes back, you sort of want to pick up in the same place without having a whole bunch of callback hells and so forth. And so a lot of the frameworks on the UIs are built around trying to make that problem easy, try to make the complexity low. So he suggests actually that if you believe in the sort of transformation streams we saw in the previous page, there's a different major pattern for how to build UIs, which is reactive. And it starts with events coming in one side, and you push them all the way through your transformations, and what comes out the other side is HTML. It's the UI, okay? And they call this unidirectional, which is in fact slightly a misnomer because it's that sort of trapezoidal thing which is unidirectional. Because what you're really doing is the user's sitting there at the UI, and they're generating a stream of events, plus there's actually a stream of events coming from the server, but just let's put all those together. So then you define that trapezoidal transformation, and it just sort of like blasts the transformation at the screen, okay? And then the user looks at what you've just rendered on the screen and goes, aha, I want to click on that. And they click on that, and the cycle just continues, okay? Does this make sense? Hopefully it does make sense. I mean, people have successfully built UIs this way, but for me, it was a mind-bending transformation of, I was throwing myself, like I said, into the chasm of JavaScript and crazy dependencies and like all this funny state and like watch out for these gotchas. And it turned into like, oh, I could build this. I'm not good at it yet, but I could imagine building things like this. And I could imagine that if I built it like this, as I assemble different parts of the application, I don't have this part of the application interacting with this part of the application in bad ways and causing it to crash, which, you know, is some of the things I worry about. So again, the reactive pattern here is that there's a one-way stream transformation from human action to the transformation to the HTML that shoots out the other side. I should mention that there's a trick that they do at the very end, which is that there's a thing called virtual DOM. Have you guys heard about virtual DOM? So imagine you have a pile of HTML, which represents the entire page that you've got, and you shoot a transformation through this thing, and now you've got a giant new pile of HTML, and you're trying to do this like many times a second. Well, you'd see a lot of flickering as the browser re-renders your screen. So what virtual DOM does is it just diffs the two, and it figures out what the smallest number of operations are to change the screen to what you just said it should be. And in fact, if it's identical, then it's a no-op and nothing happens, okay? So that makes these style of user interfaces actually some of the highest performance, lowest latency of any of them, okay? So there's various guys like the Elm guys and the Cycle.js guys who show graphs and says, if you use Angular, if you use Flux, if you use my stuff, you know, and they show that the ones with virtual DOM perform quite well, often the best. All right, so now that everyone has downloaded RX Marbles, right? Everyone's got it on your phone now. We can do some more stuff. All right. If worse comes to worse, you can watch this on the screen. But I kind of like the idea that you guys can play with these on your phone. So what I'm going to do is I'm going to walk through some of the simplest stream transformations, and then we'll sort of collectively get an idea about them, and then we can move on to more complicated ones. So here's RX marbles. Hopefully you guys see something kind of similar. And what you may not know, unless you've started poking at it, where I'm going to use first. First is easy. Okay. What you may not know is that you can move these events around to do what-if kind of stuff. So what the first operation says is, if you give me a stream that looks like this, I'm going to pick out the first event, and I'm going to output that. And then this vertical bar means that the stream closes. So what first does is it picks up the first event from the input stream and closes the output stream. You guys see why it says that? It's got the vertical bar and it's got the event number 1. But let's say I grab this green event. I can move him around. You can see that changes the output, right? But if I move him farther along, nothing happens because he already got the first one. Make sense? The other thing to note is that this application is written using reactive principles, of course. Of course, why else would they do anything different? And you'll notice that it's very fluid in terms of highly responsive, very low latency. There's no round trip to the server, none of that sort of stuff that would slow it down. Okay, so is everybody on top of what first does? Okay, what did I decide to do next? It was filter. Well, we can do last also. Last. So last gives us number 4. Now notice when last gives us number 4. See, here's where the number 4 event occurs, but then number 4 doesn't get output until later. Why is that? You can't know it's last. Yes. So when can you tell it's last? Yes. So do you guys remember that I'm going to go back to the slides real quick. Is it this? Yes. Okay. In this pipeline where ls gets piped to grep, do I need to know if the stream is closed in order to do the grep operation? No, I can do that incrementally. For each piece of data coming along, I can decide that. How about unique? Well, you certainly have to accumulate some state, right? That says, like, if I give you the number 1, I would look at my state and say, have I seen number 1 yet? And I could output it, right? If I haven't seen it. And if I see number 1 again, I could say, I'm not outputting that, I've already seen it. So it certainly is a stateful thing, but you can actually output it incrementally. But then sort, can you output anything from sort until you get to the end of the stream? You got to wait till the very end of the stream. So interestingly enough, in this example, you have something that literally can work as the, for each bit of output, you can be filtering it as it goes. Unique has to hold on to a lot of state, but it actually can do stuff incrementally. And then sort has to wait until the very end, until the on complete. All right, so let's go back to marbles. Yeah, so if we change around these guys, as you would expect, if I push 3 over here, then the last one comes out. Okay. And then I think the next one we're going to do is filter. So what this expression says is I want to filter x's, and then the sort of arrow is such that x is greater than 10. Okay, so I have events at the top which have numbers in them. And so I say, which of those things have x greater than 10? So 2 is not greater than 10, so it doesn't appear in the output stream. But then 30 does appear. And of course, if I move these guys around, they still appear. And also notice that the on complete happens at the same time, right? So I close the output stream at the same time as the input stream closes. I can't short circuit until I get to the very end. Okay? Making sense so far? All right. Which one was I going to do next? If only you guys could look at my slides and tell me what comes next. Take. Oh, take is fun. Okay. Where's take? Take. Okay. So you've got the first stream, and it says take 2. And what it's going to do is it's going to grab the first 2 events. It's going to take them and put them in the output stream and close the output stream on the second one. Okay? So that's not a big step compared to the previous one. Okay, so let's try take until. What do you guys think take until does? Part of the fun of looking at this stuff interactively and seeing examples of it that you can sort of play with is that it's a different kind of learning than if you got a mathematical definition of what take until was, you probably would stare at it and scratch your head and go, ugh. But by seeing an example and being able to play with it, it sort of engages a different part of your brain that cements it a little bit better. So what does it look like take until is doing? Can you speak up a little bit, please? Yes. So I'm going to take events from the first stream until I see the first event in the second stream, and at that point, I close the output stream. Okay? So let's try it. Let's see if that theory works out. So I could move this guy around, and it would change the output. Indeed, it does. Look at that. And we can see the little bar moving to indicate that the stream closes. Oh, but if I go past the other event, then nothing else works. And similarly, if I move these guys around, they move. Pretty neat. Okay, and as you might imagine, people have been working on this for years, and so the vocabulary of what they've got inside of here is pretty extensive. And like you might not have thought that I need take until, but if it's in the box and you know it's there, you'll probably come across a problem that says, keep doing the top one until they hit the pause button or something like that. And then you put the pause button on the second stream and it stops outputting or something like that. Yeah. Okay, what comes next here? What are we going to look at? Take and take until. Merge. Merge is fun. They're all fun, really. There it is. Okay, what do you think merge does? Without using the word merge. Okay. Yeah. So as I combine these guys, it's going to combine those guys, right? And although this doesn't show it, presumably merge would close when? Would it close when the first stream closes or the second stream closes? Probably the second stream. Both of them have to be closed because then no more events are coming, right? All right. If I had more than one word of short-term memory, I could. Oh, can you drag the endpoint? Ah, so clever. So I heard this that said the only truly intuitive user interface is the nipple. And when you think about it, you're like, probably true. All right. So let's try map. Where did map go? Here's map. Now, map is a big one. Map is like the heavy hitter of functional transformations. And anybody who's ever done programming in a language where they've got lambdas knows how this works. A lambda is a little chunk of code that says, if you give me these variables as input, I'm going to do some stuff on them, and I'm going to output things. Okay? And if you remember from math, you would have for every given value of the input, it's going to map to like one value of the output. Okay? So in this case, it's going to take each of those events in the input, the 1 and the 2 and the 3, and it's going to run it through a little function that takes the variable x, which is the input, multiplies it by 10. And so I get 10, 20, 30. Okay? Makes sense. And you might imagine that in your programs, you can write a relatively complicated mapping expression that turns it into complicated things. Something I guess I haven't stated is that all these examples are dealing with like trivially simple data types like an integer, but there's no reason this couldn't be an address or a customer record. Like you could map between an address and a GPS location, right? There's no reason, GPS isn't the right word. What am I talking about? What is the lat long, there we go. You could map from between an address and lat long, right? Or you could do the other way around, which is lat long to the closest address, right? You can imagine having servers that have a function that's stateless on them that you say, I can throw addresses at you and you send me back the best coordinates that you, coordinates, that's the word I was looking for, best coordinates. All right, and we've got one more. So what I'm showing you here is just composing several of the things that you saw before. And the composition is towards something that you want to do all the time in a program in the user interface, which is, that's great, I've got clicks, I can change the HTML, but at some point I need to go over to the server and get the new customer records and then bring them back and put them in a list, okay? Something like this. So here's the pattern for doing that, is that you have a click stream of the user clicks or something like this. You map those clicks into a remote procedure call request, like go off to the server and go get stuff. You have to send the remote procedure call and wait for it to come back. You turn the responses into another response stream, and then you transform the response stream into HTML that you push out onto the screen. Okay? Does this make sort of intuitive sense that this would work? Because what we did was we stepped outside of the closed world of the single program, and we turned, the critical idea here is that you can take the things that are going on inside my world, map them into request objects, which then in fact get turned into response objects, which then get turned into the screen, or put onto the screen, okay? Now, does anybody notice the trouble in China that's going on here? Big trouble. Little China. Is the mapping operation stateless? Is it a pure function with no side effects? Yeah, I believe that the first one is a pure function with no side effects. Okay? I could do it 20 times, I get the same output, just like I did in the little marbles diagram. And the second one, the second map operation is also has no side effects, right? But what if the one in the middle, if it executes, what happens? I mean, there's a side effect in the world. I sent a message out, right? So here's an example of a side effect. There's the military guy sitting in the bunker with a big red button that says launch missile, right? When I hit that button, I have a mapping operation between the click stream and the RPC request, and at some point, fuel starts burning and the missile starts launching, and that's a side effect in the real world, okay? And so the point is that a lot of these UI frameworks have to grapple with exactly this. In order to get the kind of work done that we want to get done, there's a phase of the program where pure functions with no side effects are used as much as they possibly can be, but then they sort of cheat in the middle at some point, and they say, what you do as a programmer is you create these requests and you hand it off to the context, the environment. And magically, as far as you can tell, without side effects, another stream gets created that you can register for that says, here's responses that are coming into your program. Okay? So the point is, as far as the world that you are programming in, there's no side effects. Okay? But you have to be aware that there really are side effects going on in the world. And so that's the programming structures, the patterns they use in the user interfaces are grappling with giving you the simplicity of the functional stateless transformations, and then they hide the little bit in the middle that makes it impure, okay? So that you can pretend like it's pure, they handle the impurity over at the side. So in other words, there's going to be side effects, but they keep them in a little box, right, that won't cause trouble for the rest of your program. Okay? Make sense? Well, at least one of you nodded, so that's pretty good. All right. All right. So I've given you a new challenge, because this happens a lot, that you've got a user interface, and it once makes calls to the server. There are some calls to the server that don't require you to be logged in, let's say hitting the home page of your application. But, if you want to see your bank account, you have to be logged in. So once you've logged in, there's this common pattern that your user interface gets this token that identifies you, and it's good for 5 minutes or something like this, okay? So what I'd like you guys to do as a design is to say, how would I think about doing that with streams of events, just like we talked about? Okay? So don't worry about challenge number 2. Challenge number 1 is, how do you build a UI that's stateless? Now, well, actually, first, let's do this. How would I do this if I was just writing regular JavaScript and I wasn't trying to be stateless? What would I do? There's a remote procedure call to the server that says get auth token, right? And when I get it, what do I do with it? I store it in a field called current auth token or something like this, right? And then anybody who wants to get to it, what do? They just say, pull, access the variable and get the auth token, right? So it's something that, like, again, for all of us in this room are going to be like, that is really, really easy. And so what I've asked you to do is transform that problem. Like, it's a different problem. Like, within this style of you've got a bunch of event streams, how would I go about doing this? So if you guys could just work, feel free to chat with your neighbor if you're friendly. Okay, I think everybody has had some fun working on this. Why don't we get back together as a group and try to solve it together? Let's imagine that we're going to start with an input stream here. Okay. How did you guys start? Like, I have an input stream, and at some point, I need to have these auth tokens. Okay. Anybody want to volunteer something they came up with? And in fact, it's perfectly okay if you just want to talk through the problem, because that'll probably help a lot of people, rather than just saying, here's the answer, which doesn't help a lot of people. Yeah.
There was a click stream that's an input stream.
Okay. So these are clicks.
Yeah, so,
Okay.
so then that calls a function that would be eventually making a call out to wherever it needs to call out to. But in that function, then you subscribe to another stream for tokens.
Mhm.
And you do a first on it and say, do I have a token? And if else there. And if the stream is empty, then you make a call and say subscribe to the completion of that. So that stream goes, gets the token. Well, that, if you don't have token, you make a call, go get the token. Completion of that function.
You've lost me. I'm sure it makes sense. You just lost me. It sounds complicated. Does anybody else want to jump in? Yeah.
So I just looked at the problem as I start a session, I authenticate, and the session just keeps staying open. That's the whole screen. And anything I do in between is just a series of events. And the result from the previous event gets passed into the next event.
Yeah. Okay. Well, how about we start with this? Does anybody? Sorry.
That would imply that you have state, and if it's truly stateless, I should be able to swap out, this executing code for this executing code.
The state would be encoded in the streams rather than in the functions themselves. There's no question that if you have a UI and it's showing the number 1, and then later on the UI is showing the number 2, there was some state change in there. But the question is, where did the state change occur? Where is the state held? Yeah, and so for example, if I say, here's my series of events, and what is the last thing in that series of events? It could be the number 3 or the number 2, right? So your function doesn't know what the state of the system is. It just knows what the streams are, and it takes the last event on the stream and puts it on the screen. Okay, so that's sort of my intuition for this problem. So let me try something here. So, yeah.
So what you're saying is really the state in this system of thinking is the collection of events itself.
Yes.
The system doesn't function unless something holds on to that collection of events.
That's right. Yeah.
Is that the way it works?
Except that I would swap out the word function for work. The system doesn't work. No, I know, yeah. So let's try this. But yes, you guys are on the right track. The functions themselves don't hold on to state. And notice that we don't have an if-then statement, right? So this is part of the trick, is like our brains are wired for if-then, and we're trying to do this without if-then. So what if I had a click stream and I've got a click in here? Well, what kind of click did I have? Let's just call this the sign in. Okay, so somebody clicks on sign in, and I'm going to ignore the fact that they type their username and password in something, but there's a sign in click. Okay, so if I need an auth token, what do I need to do with this sign-in click? Okay, so maybe I've got another stream here, which is, we'll call this the auth request, okay? Okay, so this, I'm going to map this to this with a map operation. I'm going to map every event into a auth RPC request. And I'm waving my hands about what the definition of exactly how this event maps into the request. But if I could get that request, great. Now I've got a stream of requests, right? And then we get the magic, okay, which I described before, which is this is the stuff that's not stateless, and that's the stuff that's the screen. Oh, it actually, is this just because it, there we go, back. Okay, so then there's a magic RPC, right? This is happening. And then I transform this into a stream, which is the authentication response. And that could happen sometime later, let's say back here, right? So I got that event stream. And then I need to transform that response into the auth token, right? And again, I'm going to wave my hands about this map, okay? And say this is the auth token. And I'm going to have this event right here. And this is a map operation. So this is a map. Sorry. It's going to map the response into the token. Okay? So this represents the auth token. So again, I think everybody here, the operators were on the table. They're not enormously complicated, but the thing that I continue to have trouble with is that I'm banging my head against. I can see every step when you do it, but I can't figure out, like, I haven't internalized the patterns on how to get there. But this sort of pattern of taking some input, transforming it into a request for an RPC, handing it off to the environment saying, this is going to happen, and eventually I get back an RPC response, and then this is what you would call the unmarshalling in another, like I take the response, I pull out some fields, and I create another stream that has the auth token in it. Okay, yes?
So to kind of continue to push that mindset, I mean, would you really, from an application architecture perspective, would you really think about it as a token or just an authentication event or authentication observation? I mean, if I'm kind of trying to push that forward into my application architecture, am I really depending on the presence of this map token, or am I just depending on the observation of that authentication RPC call completion as a success event or something like that?
I'm not sure I know how to answer that question. So like I said, I have giant imposter syndrome on this whole thing, and there could be a clearer way of thinking about this. So I'm sort of monkey see, monkey doing the patterns that I've learned.
Yeah, and part of the reason I ask is because, like, in a typical kind of web application architecture, right, the mechanism you're using is a cookie in many, many cases, right?
Yeah.
You know, and that's just an artifact of the specific, you know, application infrastructure that you're working with, right?
Yeah.
It's not necessarily an event in and of itself.
Right, right. That's very good. I'm not making a careful distinction, as it's often valuable to do, between events and these and the things that are on these streams. Okay, so they don't necessarily represent, like the user clicked a button and I'm holding onto a cookie can both be put onto streams, but those are slightly different kinds of things. Agreed. Okay, so now if I've got this auth token stream, I'm good to go, right? I just pick this thing up. Okay, so let's take a look at challenge number 2. Yes. Mm-hmm.
Progress through these, those individual screens that close the authorization, those close at the end of, or do they stay open?
So that's a good question. In the way I've been thinking about these, I was leaving them open. But I can imagine, for example, the sign-in stream closing. The thing is that you've got a lot of discretion about what exactly goes into this stream, right? The program doesn't care what the stream is. I put a label on it calling it the click stream. I could call it the sign-in click stream. I could call it the any clicks on the UI stream, and they're really like XY points, and I map those into, well, if it's at this location, that means this thing. So we've got a lot of discretion there. So, but that's a good question about like when you would choose to end these things. Okay.
Related to that, what's the overhead of the streams?
For the time being, let's just say like it's reasonably negligible, right? That even if, well, okay, if I just think about the size of, like even for these things that we consider small and constrained for like your phone, you've got a gig of memory or more, and like so holding on, even if you held on to all of the click stream, that wouldn't be that big. For many of the operations, you don't need to hold on to the whole thing. So for example, remember the in the Unix command line stuff, right? grep, which is filter, doesn't need to know anything about the history. So you could optimize that away and just say drop all the event stream. For sort, unfortunately, it needs to have a buffer. And so that would probably take more memory. If you wanted to stream a gig file or a music stream or something like this, that would take space. Okay. I'm going to try to wrap up the end of this exercise here. You guys are asking great questions, and so in some ways I feel like I'm succeeding just because I'm like making people aware there's another way of doing it which possibly does work and might have some benefits. It's like, okay, maybe you're going to go home and click and read these articles and say, play around with it yourself, and that's really what I was hoping to do.
Just before you go on to challenge number 2, how would you then use the token? Would you like combine the click on the events on the click stream with the last event on the token stream?
Exactly. Yes, we could just use the last operation. But in fact, it could be the first operation at this point. And so this is where number 2 becomes interesting, which is let's imagine you had something else going on inside your program. Okay, that they're trying to check my bank account balance, right? So I'm just going to call this the balance. See, I'm assuming that this is a bank that I've logged into the bank, and then I can check my balance. Okay, so there's an event. I'm running out of stuff on the right, but there's some operation that says check the balance. Okay, and just so that I can skip through all the RPC stuff, just say I know it's probably going to have to go through an RPC, but that's this. When I want to say render the balance, I would have a map operation that would say take the auth token and the balance, do an RPC, or the request for the balance, do an RPC, make HTML out of it, and put the HTML into the output stream. Okay, so that doesn't seem so hard. The tokens expiring is an interesting one because when I do the RPC to get this balance, I might get an error stream back, right? Or I could just say I can get the response, and the response might be 404. What is there? There must be a response code for authentication or something. But 401. If you get a 401 back, then you say, aha, I need to re-request this thing, and now you have another auth token that appears here, right? Well, it's true, but it's a mapping operation between the 401 request and 401 response and a request here to do. You would put another token on this stream, okay? And then because there's a token on this stream, the magic RPC happens, and then the response comes, and then we put the auth token on this stream, and eventually I would be allowed to do my RPC for the balance. So I'm sort of waving my hands because I'm running out of space both horizontally and vertically, but does this sort of, yeah, and then the idea, which gets exactly what you were asking about before, is which auth token do I use? Well, I use the last auth token in the auth token stream, okay? Yeah.
You have multiple users on your website?
My website, probably not. Like 0 is pretty much the median.
Link and associate links coming from a particular user, or they all mix it up in a sense?
That's a good question. I mean, again, this is some machinery for us to use, right? Maybe it's exactly the sign-in that gives me the identity of the user, right? It's the authentication stream. That everybody is anonymous until this happens. Another way of thinking about it is all of what I'm talking about here is I'm saying this is running in the browser, right? And so it's whoever's in front of the browser, most websites don't have a model that like you and I are both in front of the computer and competing clicks on it, right? Now when it comes to the server RPCs, that's a whole different thing. But the idea is the server is getting this RPC with my sign-in request and the credentials that I just supplied in the box that I emitted from this example. Okay? All right. Okay, how was that? Good? All right. So, it was impossible for me to figure out exactly how long to plan for this, and we've got 15 minutes left. Hope you guys have had a good time. There's about 50% more material left. You think I'm joking. So there's this guy who wrote, I can't remember his name, wrote this book called Understanding Comics. And I saw him speak, and the first thing out of his mouth was, "We better get started. I have 472 slides." And everyone went, "Ha ha ha!" He had 472 slides, and he got through the presentation in about 60 minutes. It was very effective. One of these days. Okay, so the next section is us taking a look at things you're already familiar with, architectures and patterns and styles that you've already seen before. And with the lens of functional programming, we're going to see some interesting stuff happening here. So I've divided this up roughly into client-side, server-side, persistence, batch, sequential, and DevOps infrastructure. It's an organization scheme, so I can divide it onto slides. It's imperfect. But we've already been taking a look extensively at these reactive patterns. Okay, there's another idea called serverless, and there's sort of two variants of this. In Mike Roberts' paper or essay, he talks about this idea that imagine you had your regular 3-tier system, okay, with your stateless middle tier. Okay, just as a thought experiment, what if I took the stateless middle tier and moved all that business functionality over into the web browser, into your client? Like, that should be possible, right? Because it's stateless, and the browser's fast now. Well, then it's like, his point is, wow, that sort of sets things on your head because it makes it a lot easier to deploy applications. You already have to have an ability for a user to download the app into their browser. Well, now the browser directly communicates over to your database, and it communicates to your auth infrastructure, and it communicates to anything else that you need, okay? I'm not saying it's for everyone, but it's an interesting pattern, interesting idea. On the server side, we already talked about stateless middle tier, which is a pretty standard pattern we've been using for a long time. We talked a little bit about immutable state and resource versioning rather than mutation. This can be a very handy pattern with REST, so your customer gets version 1, 2, 3, 4. Any given version of the customer stays there forever. There's another variant of what's been called serverless, which is that if you think about your stateless middle tier, why are you deploying a special server called, my bank account balance function? Why am I doing that? When I could just say, here's the function and host it, okay? So Amazon has some facilities for doing this kind of thing, the AWS Lambda. And so I think the big benefits here from an operations standpoint are, you're not hosting a whole bunch of servers specifically on something. In my head, the idea is you hand it the jar file on demand. Say, here's the function I want you to be running, okay? The last one here is on the server side. We looked at the client side already, but reactive services and transformation operations can be working on the server side as well. Instead of very large applications that take in something, crunch the numbers for a very long time, and then end up doing something with it. Increasingly, people are breaking it up into smaller and smaller services that do simple transformations, right? So like we talked about addresses to lat-long coordinates, okay? So if you could chain a bunch of those things together with events streaming between them, you can end up with a nice responsive server, or system, I guess I should say, and you can tune the number of each one of those instances that you need to the size. We've talked a little bit about persistence, and I can plug Sebastian's talk like everyone's doing today. That we can have immutable and version data. We talked about the HTTP cache duration set to infinite is a very convenient thing for your system. There's an idea of append-only data stores or event sourcing, where the idea is that if the data on the disk never changes, it only continues to grow. That's a constraint, but maybe I can use that to my advantage, right? That if I never have to worry about it going away, then you can reason through what's on the disk much easier. A log of events that just keep accumulating, you can do transformations on those. And this morning, the keynote was about CQRS as well. So batch, sequential, and pipeline architectures are things that happen at a very large scale. As you guys know, if you're in an individual program, you might have the observer pattern, right? But at the architectural scale, you can have event-driven architectures, okay? And those things are cousins of each other, just at different scales, okay? So the same thing goes on when we talk about batch sequential, is that when I'm doing things in a series, or if I'm streaming data through them, we have different names for the architectural patterns on those. In fact, the MapReduce architecture, which was popularized maybe, quite a while ago now, map and reduce are two operations you often see in the small. We saw map today, but reduce is the same kind of thing. And the idea was, well, we've got these gigantic internet-sized data sets. Maybe we can apply mapping and reducing operations across all of those. So another example of things that we're programming in the small appearing in programming in the large. And then finally, what's maybe more appropriate for today's newer stuff is that increasingly we're doing all these machine learning pipelines, okay? And the machine learning pipelines take an input, say like it's an image, and the output is a classified, what kind of image this is. Is it a cat? Is it a street sign or whatnot?
After the machine has learned.
Yes, let me be clear. What I'm talking about is the output operational network as opposed to the back propagation part of the learning part. And that's about as far as I can go on the machine learning part, unfortunately. Did that too long ago. Okay, the last little bit that we can see here is in terms of DevOps infrastructure. We're already familiar that every line of source code we write is checked into version control, right? 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 Even the scripts, right? And so if I now write scripts for deploying the architecture or deploying the system, then I check that into version control, right? And if I've got code that tests, of course I check that into version control, right? Okay, so now I've got everything checked into version control, including the scripts, including the tests, including the deployments, okay? I've got all that stuff in there. So that's kind of an append-only data structure that gives me certain properties, right? That I can always go back and rebuild any configuration that I've ever had because I appended only. I didn't mutate. Like if I'm in my IDE and I just press save on a file, it mutates the file. But when I check it into version control, it doesn't mutate the file. It ratchets it forward and keeps the old version, right? So this is just another example in the DevOps context of those append-only data structures can be very valuable and give us certain properties. We can always go back to them. The next idea here is the so-called immutable and idempotent infrastructure, which is if you have a system that's running and you want to change it, you do not go to any of the instances and change a parameter on them. Instead, you start with your version control system because you've got everything checked in, you change something there, and you push out a new copy of the system, okay? Now, yeah, I'm not saying everybody should do that, but there's examples of times when that's very helpful. Okay. We're not going to get to do a group exercise in using functional programming. So let's do this very quickly, which is that if we had, this is just the traditional 3-tier system. I have a library, and I want people to be able to come in and check out books, okay? My thinking is how people commonly do this is you'd have some number of clients, okay? And you would have some sort of middle tier, and you'd have some sort of database, right? I'd actually have a bunch of these clients, and I'd probably have a bunch of these things, and maybe even my database is replicated. But just for the time being, let's assume one client connected to one server, connected to one database. And when there's an operation that's something like checkout, so he's going to check out book number 1. What's going to happen is that request is going to flow through the system. There's going to be some sort of database table in here. And what I'm going to do is I'm going to update the records in the table, and you're going to mutate things, and then give him a response back that says this book is checked out. if somebody comes in and says instead, I would like to check out that book, it'll go in here and say, oh no, it's already checked out to somebody else. You can't check it out, okay? So what I was just trying to point out is that we're very used to doing this kind of architecture. Okay, so the question would be, I think we've talked about a bunch of different patterns here, and to this point, let's just brainstorm and say, how would that architecture change if I wanted to try some of these different patterns? So I can try the first one, which is the reactive client. We went through a significant design exercise here, and we got a flavor for how those reactive clients would work. I don't think that would ripple into anywhere else, into the UI, from the UI into anywhere else, but the UI itself might be designed quite differently. Okay. What about the reactive server? How would you guys think that the reactive server might work differently than with the traditional way that I build the middle tier? Well, if you think about it as a function that maps A to B, what might A and B be on your server if I said check out a book? So the input might be a request to check out something out, and what might the output be? Yeah, like in the old days, they would, oh my God, I'm dating myself. Do they still have like the little cards inside the books that you write on? Okay, it's been too long. I know that card catalogs are gone. I had that conversation recently. Okay, so you might imagine the server taking in a request and giving back something like the reservation for the book, or the record that represents the loan of the book to you, okay? And if you were doing REST, you would actually be getting back the URL of the loan object. And anytime you wanted to query that loan object, you'd be able to see it, okay? But your server then just becomes a transformation where it picks up the request, it does some work, and then it hands you back the response, okay? Which again is not radically different than what you're doing before, but you might think about it slightly different in terms of it's a transformation between A and B, okay? How about stateless server functions? Well, the one we just described here, we could do that statelessly, right? I could have a bunch of stateless things. I could even imagine having some anonymous host of servers that I can deploy jar files to that get the stuff done. How about event sourcing or an append-only database? Is there any value in that in this kind of problem? You're nodding your head. What do you think?
Yeah, reserving the books so that nobody else can actually load it at the same time. Instead of making a reservation record, just as an event.
Yeah, in the old days, there's this there's a card, right, that sits in this this little pocket in the front of the book. And what the librarian does when you bring the book up is they physically remove this card, right, and they write some stuff on it that says, Eltjo just reserved this book and the date, and they stick it in a filing cabinet, right? And when you bring back the book, they reunite the card with the book, right? Some physical system, right? So they put some notes on this thing. Okay, so if I was doing this in a purely electronic way, is there any equivalent in terms of the event sourcing or the append-only database? Is this card kind of like an append-only database? Right, okay. And if I wanted to ask a simple question, like I'm a librarian, I'm looking at the librarian view of the UI, I want to know things like what books are checked out right now? How would I find the books that are checked out? So tell me more. How would that work?
Yes, sir. So if I'm writing a ticket card, so if my books are like ongoing events and appended database, then the last event will tell me it's checked out by someone or something.
Okay. Yeah. You could imagine a stream of all the check-in, check-out events, and that there's some mapping that goes along, and it removes all the events that, for if there's a check-out and a check-in, then you drop it from the stream kind of thing. So then your output stream is all the checkouts that don't have a corresponding check-in or something like that, right? So one of the things I can mention is that when you say that out loud, it sounds like, you've got to be kidding me. Like that sounds like such an expensive operation. But a lot of times there'll be checkpoints along the way so that you can say, I don't have to go back to the beginning of time. I can checkpoint it, and then at some point I just need to compute the delta since the last checkpoint. Think about your bank account balance. Actually, we should just come to Sebastian and talk later. But your bank account balance, they could literally, every time you ask for your balance, sum every operation, right? Or they could just keep a cache of it and say, when was your balance last computed? And if there's no transaction since then, they just hand you back your balance. Okay? So there's ways of making these things that seem so crazy a little less computationally intense. Sorry? Listen to that man. Okay. Well, yeah, but they're supposed to ask questions, right? Well, that's right. You've been asking questions all along. Okay. So the end of the boring slides. Only one slide here. So in conclusion, we started out with this idea that many of you, certainly me, I had put the ideas of functional programming, logic programming, OO programming, procedural programming into the bucket of programming in the small. Because that division had been set up back in 1975, saying this is the way we're going to treat these two topics separately. But whether it's functional programming having the effect on architecture, or whether it's just good ideas that end up popping up in two different places, it doesn't really matter. But what we can see is that things like function composition, pure function, statelessness, and immutability, idempotence, and declarativeness are things that have already popped up in our architectures. And if we start thinking about the problems that we're facing right now in a slightly different way, you can imagine applying these things in new and in innovative ways that are relevant to today. Especially as we talked about the motivations for computing being incredibly cheap, but in constrained ways where you can have lots of individually, I'm going to call them slow computers, but you can't have one 100 gigahertz computer, but you can have a bunch of 3 gigahertz computers. So there are a lot of advantages, especially for distributed systems here. From my perspective, I was most shocked by the changes in how you build user interfaces, and that was that design exercise we went through with the unidirectional flow rather than a big, complicated, mutating MVC graph, which is the way that I got used to doing things. And what I would really love, and Michael Keeling was the one that pointed this out, is that what we really would like is a catalog of tactics. If you're familiar with the SEI taxonomy of you've got architectural styles, and then sort of at a slightly more granular, smaller level are the tactics. Each one of these things doesn't feel like an overall architectural style, like I'm doing the immutable architectural style. No, but I am using immutability in a certain place as a tactic to achieve a certain kind of architectural quality out the other side. I would love to see some work on that. So in your SATURN talks for next year, these would be great things to work on. At least I would love to see them. All right. Well, that's it for me. Thank you guys for showing up and being such good sports. Please play around. Oh, there's one last slide. There's a bunch of references here. Please play around with the example apps and check out the references. And let me know, as I'm still a newcomer at this, let me know what I got wrong and what else I should be reading. Thank you.